My name is Doug. I'm a developer advocate with the Firebase team at Google. You are here right now, obviously, because you have something to do with Android, or you want to learn about Android, which probably puts you somewhere on the front end side of software development. If you do front end stuff, it's a really good chance that you might also not want to do back end stuff. Because if you operate across the full stack of technologies, you're going to have to keep a bunch of things in your mind at the same time. So you've got a variety of languages between front end and back end. Some of these you might be familiar with, others maybe not so much. If you work across the stack, you've got to keep different operating systems in mind. So obviously you're working on Android on the client, maybe you're working in Linux on the back end, or maybe even some other operating system. And between all of those, you probably have some frameworks that you have to learn as well. So on the front end, the Android team encourages you to work with Android Jetpack as a framework to build your app. On the back end, maybe you have different frameworks. So if you're building HTTP services on Node, you might have to know something about Express, or if you're doing classic Java backend development, J2EE has been around for a long time. There's a lot to know here. There's, between the front end and the back end, full stack programming makes you think about a lot of things at the same time. What I don't like about backend development, though, is all the work that you have to take to configure your backend. So in traditional backends where you manage the machine, you have to, of course, configure the machine, which is time consuming, a lot of effort to do that up front. Then you have to maintain it. So you have to do things like tune it, update with patches, generally do upgrades. Not a lot of fun to do. And of course, when you want to send your app to production, you have to worry about scaling it. So one server is never going to be enough under load. You have to figure out how to get lots and lots of servers up to handle the load, and also how to scale them down when they're no longer needed, because you don't want to pay for all those servers being around all the time. On the front end, we really don't have any of these problems. On the front end, you have a different set of problems, which I think for someone like me is easier to manage. Like, I can actually deal with the differences across API levels on Android devices fairly easily. Doing backend stuff is not so easy for me. But fortunately, Google provides software products to deal with stuff on the backend so that you don't have to. So Firebase as a whole is a platform that helps you build better apps, improve the quality of your apps, and grow your user base. All of these products pretty much are invoked directly from the front end. There's no back-end management to do. And in particular, the apps on the left-hand side here under the build category provide a lot of the framework or infrastructure to do back-end development. So here you have user authentication, you have some ways to run back-end code, you have NoSQL cloud-hosted real-time databases, cloud storage, all these tools you can use to put together to build an app without managing any back-end. In particular, the three tools that I use most often are Firebase Authentication to get users signed in, Cloud Firestore, which is a cloud-hosted NoSQL real-time database that you can access, again, directly from the client, and Cloud Storage for uploading and downloading files. Since these are all invoked directly from the client, you don't write any code on the back end. At least you don't have to get an initial app running, though you can add your own back end. You will need a backend for some things like payment processing. You probably don't want to trust your client app with all the information required to make a purchase. You probably want to keep a lot of that logic safe and secure on a backend. Same thing with game logic. If you're worried about people cheating in your game, you probably want to keep that logic in a place where it can't be compromised. And also things like data validation. And I'm saying all this should go on the back end because you really can't trust what happens to your APK after it gets installed on the user's device. APKs can be broken down, all the logic can be extracted from it, the APK can be rebuilt and executed the way that the user wants. So in short, you should assume that malicious users can change the way your code works on the front end, and that's why we need some back end stuff. Also, if you want to schedule periodic work, that's probably best done on a back end because you really can't trust that a client device is going to be running all the time. And of course, if you have lots of batch data to process, you probably don't want to put any of that on the client because clients just don't scale in a way that facilitates massive amounts of data. So if you're a front-end developer and you need a back end for any one of these reasons, excuse me, you probably have some preferences about what you'd like to do. Of course, you'd want to minimize the time and effort to a solution. So whatever you end up working with in your backend has to be relatively fast, has to be easy. You want to minimize maintenance. Like I said before, maintenance on backend servers is really kind of a pain. It subtracts the time that you take from actually building out your app. You probably also want to make use of things you already know. So if you already know things like Java and Kotlin, if you're familiar with the JVM, if you'd use Gradle for builds and Dagger for dependency injection, you'd like to reuse as much of this knowledge as possible. And you can, of course, if your backend is implemented using sort of a JVM-based system rather than some other runtime. But in any event, if you are going to build out your own backend, you will have to learn something new because backends just don't run Android, right? You can't use everything you know about Android. You'll have to do something in addition to what you know now, but you probably want that to be as low friction as possible. Now, it's my opinion that the easiest backends that you can work with are called serverless backends. Serverless is kind of a buzzword that's been around for a while. What does serverless cloud computing mean? Well, pro tip, there are still servers. You can't get rid of the servers. They're always there, right? But the difference here is that you don't have to manage or maintain them. The servers are there, but you don't have to worry about licensing, installation, any sort of maintenance and support. All of that is taken care of by the cloud provider. What you do is just pay for what you use. So instead of paying for servers to be up 24/7, what you're doing is paying per invocation of some code or some function on the back end. It also handles scaling too. So if you aren't using any resources, you pay 0. The moment you start using resources, those resources scale up and you pay only for what you use. Also, those resources will scale down if you're not using them. So all of that is handled completely 100% by the cloud provider. What do? Well, you just write and deploy code. That's your only responsibility in a serverless system. Now you have 3 main options provided by Google. Of course, there's others. I work for Google, so I have to talk about Google, right? So the first thing I'll point out is there's a product called Google App Engine. It's actually been around for quite some time. Google App Engine was launched 10 years ago. It was the very first Google Cloud product. Of all of the pantheon of products we have now, this was the first. You can choose a backend in either Python, Go, Java, JavaScript running in a Node environment, or PHP. So you have some options to work with. What you do with Google App Engine is build a traditional REST API backend. So the idea is your client code is just going to invoke the server code that you've written exposed through API endpoints. But the special thing about Google App Engine is it provides a number of backend services that you can use. So it's not just writing the code to satisfy the endpoint. You also get tools like databases, memory caching, storage, search and indexing. All these tools are readily available for you to use in the backend code that you write. But you should be aware that it has some limitations. Since this product is 10 years old, it doesn't do a lot of what more modern cloud products do. That said, it's still relevant, it's still useful. A lot of Google Cloud technology is still built on top of what App Engine started with. But there are some things that just don't work the way you'd expect. In particular, if you're targeting Java, the Java runtime isn't quite exactly what you expect from like a normal Oracle JVM. In fact, the way that it does threading is a little bit different, so you have to make some concessions in your code to handle that. Anyway, Google App Engine is out there, it's useful. I don't think this is the first best choice. I think one of the more newer and better choices for implementing a serverless backend is called Cloud Functions. With Cloud Functions, what you have is functions as a service. The unit of deployment is the function. You are basically just writing units of code that get invoked. There's no fancy architecture. There's no like massive frameworks to use. You just write function code. There's 2 things you can implement. You can do HTTP endpoints, just like App Engine. So if you define an HTTP function, you basically receive the request and send the response. Pretty straightforward stuff. But the special thing about Cloud Functions is that there are product-specific event triggers. So if you are using other Google Cloud products and those products are capable of emitting events, you can have Cloud Functions code trigger on those events. And I'll say a little bit more about that in a bit. With Cloud Functions, you can target JavaScript running in a Node.js environment, Go, Python, and Java is actually in private alpha right now. I believe there's a sign-up form somewhere. I actually don't know the status of this. As an Android developer, I'm sure you're far more interested in Java than, say, Node, but this is the state of Cloud Functions right now. Now, since I work with the Firebase team, I actually use a layer on top of Cloud Functions called Cloud Functions for Firebase. So it's worth making clear that Cloud Functions is a Google Cloud product. It's not a Firebase product. What Firebase does is it adds tools and APIs on top of it that we think are easy to use for mobile developers. So what you get with Cloud Functions for Firebase is a special CLI. There's the Firebase CLI. There's automatic setup for JavaScript and TypeScript, so you can set up your project using one or one or the other, and it all runs in a managed Node.js environment. Now you're thinking, oh, this is great, but I don't want to learn a new language. I've heard bad things about JavaScript, right? And that's understandable, right? But like I said, anytime you're doing back-end stuff, sometimes the best solution is one that you'll have to learn something about. But I would love to tell you today that TypeScript is a better JavaScript. Now I'm going to go on record saying I don't really like JavaScript. It doesn't scale in terms of development effort. I don't like that it's loosely typed, in fact duck typed, and you can inherit all kinds of strange bugs and performance problems. But TypeScript remedies a lot of that. I love TypeScript. So if you're interested in learning something about JavaScript on Node, consider TypeScript. It has a sophisticated static typing system. So you're getting a lot closer to what you're familiar with Kotlin and Java and even Swift. It's sort of in that same tier of sophistication. You get generics, right? Everyone loves generics. Being able to say what type of thing is in your list is a huge win. And just having a list or even just an array in JavaScript is kind of painful if you don't know what's in it. There are interfaces, so you can shuttle around objects not knowing much about the implementation details. Maybe the best thing is nullability guards. So with TypeScript now you have Kotlin-style checks for things that should never be undefined or null. The language will help you understand where you've gone wrong in terms of nullability before it's ever deployed. And there's also community support for existing JavaScript modules. So if you're using JavaScript and you like some core JavaScript modules, you don't have to necessarily interact with them in terms of JavaScript. A lot of module providers are actually providing TypeScript bindings on top of their existing JavaScript, so you can use the modules in a way that makes sense to a TypeScript developer. So if the module provider doesn't provide their own, sometimes the community will provide some for you, and that's the project called Definitely Typed. So look that up if you're interested. Now, how close is TypeScript to other languages you might know? Well, here's a standard looking Java object, a rectangle with a height, the width, and a label and a method on it. What does the equivalent TypeScript look like? Almost line for line equivalent, except we have a few keyword changes. You'll notice that the types come after the members instead of before, kind of like Kotlin. You can see that there are this keyword is still there. You can see that methods are generally similar. There's the notion of public and private members. So all things considered, jumping to TypeScript from Java is not that big of a deal when you're just worried about things like how do you define classes. Now, if you want to make use of this class in Java, we'll new up a rectangle. We can access its properties. Actually, it accesses properties via methods. We can also print it out. In TypeScript, it looks, again, very, very similar. We still have a new keyword. You can see, though, that TypeScript offers, and it's hard to see here, there's single backticks on the string. That lets you do variable interpolation, kind of like Kotlin. And as you know, if you do Kotlin development, you can compress all of this down into something much more tiny, right? With data classes. Actually, this isn't even this is a data class. Actually, no, it has a method, so it's not a data class. But you can see that the code becomes much more terse when you're dealing with Kotlin. But all things considered, the differences between these three languages is not that big. If you can read Java, you can probably also read Kotlin, which means you can probably also read TypeScript. Just getting used to some minor changes in syntax and also making some concessions for the way JavaScript works internally, you can pretty much bang out TypeScript within, I would say, it probably took me about a month to really become truly proficient in TypeScript. You can get stuff done within a week, I would say. So the overhead to learning it is not so bad if you're already familiar with Java or Kotlin. Now, the other good thing about TypeScript is because it's strongly typed, you can now build IDEs on top of it that help you in the way that you're used to with Android Studio and IntelliJ. So this is a screenshot of a IDE called Visual Studio Code. It's made by Microsoft. TypeScript is made by Microsoft, actually. You can see this looks like every other IDE you've ever used, right? You have a project structure on the left. You have an outline for what the current file looks like on the bottom there. And in the main area, you have an editor that looks very similar to what you'd be used to with Android Studio. And in particular, you'll notice that as I'm typing code here, I type that dot, and since TypeScript is very aware of everything that's in the object I'm working with, I get autocomplete options, right? You don't really get this in JavaScript. Well, you kind of get it, right? But it guesses based on other strings you've typed, other symbols, and they're not necessarily strongly matched to the context here. But here, we know exactly what the options are. And if we choose that update method at the bottom, then it'll autocomplete and now give us some a description of what this method does. So what you're seeing right here is the reflection of type doc inside the IDE. So type doc is a lot like Java doc. It's inline documentation. So here this module has provided type doc that tells you exactly what's going on in this method. So you can see it has 2 parameters, returns a promise, which is how you do asynchronous programming in JavaScript, and a description of everything that's going on in here. So this is very, very helpful. I work in Visual Studio Code much the same way that I work in Android Studio. I switch between them fairly seamlessly. Now, if you're interested in starting to use TypeScript or JavaScript to build functions, you can build direct invocation functions. So I mentioned there's HTTP type functions. With HTTP functions, when you're using the Firebase APIs, basically it emulates Express.js for simple functions. So if you already know something about Express.js, which is the HTTP framework for JavaScript, you already know its request and response objects. And there's nothing so special in here. It's just the HTTP request, the HTTP response, deal with it in the way that you're used to with other libraries. Now this is for if you're defining a pure, just regular HTTP function. If you want to get more sophisticated, you can build a whole Express.js app and hand that off to Cloud Functions, and it will serve that entire app with all of its routes and all of its middleware and all of its everything that you've configured in that app. So you have some flexibility here. You can either build simple functions or you can build more complex apps. If you want to build a simple function, it'll look something like this. So you can see here that the first line is a TypeScript import. So that Firebase functions module, that's provided by Firebase to help you build out the description of your function. So what we're doing here is, and I'll read it from left to right, we're defining a function called echo. We're using the functions SDK to say we want to build an HTTP function, and when that function is requested, we're going to get a request and a response object. And those are going to behave just like Express.js. So on the first line of the function, we're pulling a message out of the query string, and in the next one, we're sending a response back, echoing that message back to the client. So not really sophisticated stuff, but enough to get you started. Now, if you want to deploy this code, all you have to do is type Firebase deploy. So if you have the Firebase CLI, that's all it takes. There's nothing else. That CLI will go off and do some work and show you what the URL is that was created for you. So you can see here the URL is based off of the deployment region. So in this case, it's US Central 1. That's Google Cloud speak for a data center, I think, in Iowa. Your project ID is in there, and the name of the method becomes the path. So this URL belongs to you. You can invoke it, so you could use curl on it, invoke that function. Here I'm passing a message of hello, and it's echoing it back to me. So not a real sophisticated example, but you can get from nothing to a fully deployed function in a matter of minutes as long as you have all the tools installed already. So that's pretty valuable. So this is a simple HTTP function. It's worth noting that Firebase adds another wrapper around that called callable functions. So it's a convenience wrapper around HTTP functions. They don't do anything that an HTTP function can't do, but what it does is it provides SDKs on the client and on the server to make invocation of an HTTP function even easier. So the SDKs will automatically handle all of the details of the HTTP protocol. So if you don't like dealing with request and response objects, if you don't want to deal with headers and content bodies and all that, that's fine. These SDKs do all that work for you. On the client, also, if you're using Firebase authentication, it will automatically grab a user ID token and send that along with the request. We'll also send the device token ID for Firebase Cloud Messaging. So if you need to target the calling device with a cloud message, you can do that very easily. On the client, it will also serialize an input object as JSON. So it handles the serialization of whatever it is you want to pass to the function. So maps, lists, primitive types. It uses reflection to discover what's in that object and pass it all up as JSON. Then on the back end, it will automatically validate that auth token to make sure the user is who they say they are. It will deserialize that input object from the JSON and give you a JavaScript object that represents all of its data. This is actually a lot of work that it's doing for you automatically. This is probably about well over 100 lines of code on both the server and the client. And what it looks like is this. So in the function, if you want to declare a callable function, you can import the SDK. Declare a function called sum. Instead of on request, we say on call. So when this function is invoked from a client app, what we can do is get an input data object that describes what the client sent and then return some data. We're just adding in the A and B properties. So again, not real sophisticated. But the interesting thing here is if you want to invoke this from your Android app, all you have to do is declare what the input object is. And here I'm creating a map with an A and a B property with number values. I'm going to use the Firebase Functions SDK on the client, get an HTTPS callable by its name, and simply call it. That's it. That's the one line of code that invokes this function. Now, of course, you want to get that response. So it turns out this call method is asynchronous. It returns a task object, kind of like a promise if you're familiar with JavaScript. You can attach an onComplete listener on there, and that the onComplete listener will give you the result, the object that was returned from the function. Now, all you have to do is reach into that. Here, we're making an assumption that it's returning me a map, and it has properties A and B. It has a property sum, which is the sum of A and B. So that's about it. And of course, you should always handle errors, so be sure to do that. So now you can see that, again, you can get from function to client invocation of a function really, really easily. There's not a whole lot to write here. Basically, the details are in, of course, describing the input object, describing the output object, and figuring out what you need to do in the function itself. All right, so that's HTTP and callables, direct invocation functions. To me, Cloud Functions is more interesting when it comes to event triggers, which we sometimes call background functions. These are triggers that are invoked in response to something happening within your project, not from within the client. So what you do with a product event trigger is this. You have to say which cloud or Firebase product that is emitting events. So something is changing in that product and you want to write some code for it. You just have to identify the product, identify the type of change you want. So for example, with databases, it could be create, delete, update. You define what it is that you're interested in, and usually some pattern to match for that change. So once you know all of these three things, what you can do is, once you've deployed this function, it will trigger asynchronously as that change occurs. So a picture on, well, I haven't got to the picture yet. If you're curious about which products actually implement some triggers, here's just a handful of Cloud and Firebase products. There are actually much, much more that trigger events, but these are the most interesting ones. You might be using some of these products already today. So for example, most apps are using Crashlytics for crash reporting. A lot of people are using Google Analytics for Firebase to understand user behavior in your app. So Firebase Crashlytics will emit events when a velocity alert happens within your app. For Google Analytics, it'll emit events whenever there's a conversion event that happens within your app. So a conversion event is typically seen to be like a high value action, like buying something. The ones that are more interesting to me actually are Cloud Firestore and a real-time database. So Cloud Firestore, I mentioned, is a NoSQL cloud-hosted real-time database. It's document-based, so you can trigger some code anytime a document is created, deleted, or updated, and I'll show you an example of that. But this creates some very interesting ways to build out the functionality of your app without writing any code in your app. You can do it all on the back end now. Now, when I say that Cloud Functions is event-driven, the way that it works is like this. You have these products. They are going to emit events that match the patterns that you've determined. All of those events get corralled inside the Cloud Functions product. Internally, it's using Google Cloud PubSub to send a series of events. And each time one of these events is seen, it will trigger your function that you deploy. And that's about it. And this is what it amounts to. Of course, there's a lot going on behind the scenes, but this is the conceptual model for how Cloud Functions works. So if you want to write a Firestore trigger, so I mentioned before Firestore is that real-time document-based database. Here's what we can do. We can use the Firebase Functions SDK and declare a function called emojify. So we're saying Functions SDK in the Firestore product, when a document that matches this pattern, and this pattern is saying anytime a document is created within the messages collection. So you can think of collections as organizing units. Documents are kind of like rows inside of a table. They contain key value pairs. So when one of these documents is created, we'll get a snapshot. And that snapshot describes the contents of the new document. We can reach into it and get a raw JavaScript representation of that document, and if this document exists, which it will and always in this case, we can reach into the properties. So imagine there's a property called message on there. It's a string. What we can do is take that message and do something silly with it, like replace all the instances of the word cat with a cat emoji. This is a very, very silly, trivial function, but it's fun, right? It's an easy to understand example. So we'll replace all the cats with emojis and then write that back to the document. So now what we've done effectively is create a sort of like moderation system. We can look for things in the document that might be interesting to change and then just go ahead and commit them. You wouldn't want to trust the client to do this. The client could do this wrong. Or maybe you want to change that logic at the drop of a hat. Again, client code is not the best place to do that. Server would be better. So you'll notice here one interesting thing is that the keywords async and await. This is how you do asynchronous programming in TypeScript or modern versions of JavaScript. If you understand Kotlin coroutines, this is very similar. So what we're doing by declaring this function async, we're saying this function is going to return a promise, and that promise is going to resolve with the result of the work sometime later. It's kind of like deferrable or deferred in Kotlin. The await keyword is much like calling the await method on a deferrable, basically saying return a promise only after this completes. Async await makes async programming super, super easy in JavaScript and TypeScript. I strongly suggest that you learn it if you go this route. Again, if you understand Kotlin coroutines, this should be fairly natural. So what you have to know to use Cloud Functions for Firebase, you will have to know some minimal Node.js and NPM. So if you, NPM is Node's way of getting external dependencies in your app. So if you know Maven and how Maven coordinates integrate third-party dependencies in your app, NPM is the same sort of thing. You will have to learn some JavaScript or TypeScript, and again, I recommend going with TypeScript. And you'll have to learn some asynchronous programming with promises. Again, it's going to be quite different than what you know for Java, but it'll be similar to what you know for Kotlin. If you're going to write HTTP functions, you'll have to know a little bit about Express.js, minimally just that request and response object, so you can understand what's coming in and how to send a response. And you have to know a few Firebase CLI commands. And that's it. This is the barrier to entry for Cloud Functions for Android developers. I would say, all things considered, if you go through the documentation, a code lab, and some sample code, you could hit the ground running in a week, I'd say. It shouldn't take you any more than that to get a basic sample running. Now, if you do want to learn about Cloud Functions, there's a bunch of resources here. The documentation is quite good. The video tutorials, go watch those only if you've enjoyed listening to me talk, because the videos are all me. It's a shameless plug. So if you don't like listening to me, don't go watch the videos. Skip the videos and go to the documentation in the code lab. But anyway, these are all good. These are all good resources. I've written a lot of code in my GitHub that works with Cloud Functions. I like Cloud Functions a lot. I'm going to say I'm biased, not just because I work with Firebase, but it's actually a very fun product to use. So that's Cloud Functions. Your third choice for serverless programming at Google is something called Cloud Run. So with Cloud Run, it's also serverless. There are no servers that you manage, but what you do have to provide is a Docker image. So if you haven't worked with Docker, this is going to be the thing that you have to learn. If you do know Docker, this should come very easy. You're basically creating your server image from what the Docker file tells you to build. You can also implement HTTP endpoints. In fact, this is pretty much the only thing you can implement. There are no background triggers. There are only HTTP endpoints. But the good news is that you can use pretty much any language and framework that you want. So you're basically not limited to the options that you have with Cloud Functions. You can bring any sort of backend as long as it's running an HTTP server. There are no product triggers, like I said, but what you can do is bridge the events from Cloud Functions into Cloud Run. So it's perfectly conceivable to write a Cloud Function that does nothing but grab all that event data and pass it into Cloud Run through an HTTP request. And the big news here with Cloud Run, it was just promoted to GA. So the last time I gave this talk, Cloud Run was in beta. Today, it's a fully released cloud product. So I can wholeheartedly recommend that you use it now. Now the question you might be wondering is, can I build a backend with Kotlin? Yes, you can use Kotlin on the backend just like you would in your Android app. The steps to get this up and running is, first, you need a build.gradle for your Kotlin backend. So if you know Gradle, this should be pretty straightforward. We're using the Kotlin plugin, and we're using another plugin called Application. In Gradle, the Application plugin lets you build basically command line apps, things that run from the Java command line. So what we're going to do here is pull in the Kotlin standard library and also a web server called Ktor. Ktor is a Kotlin native web server that runs on top of Netty, which is a sort of a long-standing Java network framework tool. So these are the two things minimally that we'll need in order to work with Kotlin on the back end effectively. Then we need to define where the main class is. So the main class is similar to anything in Java. This class has a public static void main that accepts command line parameters. You need to say what the entry point is. Once you've defined the entry point, what you have to do is tell it how to build a jar file. We're going to build one big jar file with the main class that we specified in the application configuration, and then we're going to pull in all of the dependencies. So everything that's specified by configurations.compile class path, we're going to collect all of those into one big Uber jar. And that's what will get deployed to our image, or our Docker image. The next thing you want to do after you have a build.gradle with some code is you'll need a Docker file. This was new to me when I first started learning Cloud Run. I had never done anything with Docker, but the only thing you need to understand is that a Docker file builds the contents of a server image that will get deployed. So a minimal Docker file to get a JVM running on the back end. The first thing you'll need, well, you don't need to do this, but this is the way it was explained to me, it's good to do. You need to find an image that says how to build your code. So in this case, we're going to build an image based off of Gradle, and this is going to be the build stage of our Docker file. Then within the build stage, we're going to take that build.gradle, copy it into the image, copy all the source into the image, then run the Gradle command to build it, and that's it. Now what this does is we now have a virtualized instance of just our code that's been built. It can't run yet. All we have is just this jar file that we need to do something with. So we're going to build a second stage. In the second stage of this build, we're going to use a JVM image that runs OpenJDK. In this case, it's OpenJDK 8. You can use 9, 10, 11, 12, whatever you want. You just need to find an image that suits your code. There are tons and tons of examples. You don't have to know all this. Mostly for me, writing a Docker file is a matter of copying what someone else did and then tweaking it and making it work. Kind of like working on Stack Overflow, right? So our new image is going to run a JVM. We're going to copy the jar file from the builder image into this image. We're going to put it in a file called /app.jar, and then we're going to invoke it with Java. And that's it. That's all you need to say. This is a minimal Docker file to run any sort of JVM code. It doesn't have to be Kotlin. It could be anything where you have a app.jar that was built from your prior build step. So what this is going to do basically is build a server image that when it's started will run the Java main class, which is going to start KTOR, which is going to start listening on port 8080, and then it will receive requests directed through Cloud Run. Now you might be wondering, how do I get this HTTP server up and running? I need some code for that. That's easy. Here we have a sample class with essentially a public static void main, but with not so many words on Kotlin. So inside the main function, what we're going to do is figure out which port we want to listen on. I'm using the environment here because Cloud Run defines an environment variable that you should be using as your port to listen on, but in all practical purposes, it will be 8080. Then we're going to use a KTOR function called embedded server. We're going to tell it that we want to run on top of Netty. That's an implementation detail. That's nothing you need to know about. But what you do need to tell it is what port you want it to listen on. And then inside this Lambda right here, we're going to use a Kotlin Fluent API. So what we're going to do is say, hey, KTOR, here's our routes. Here's all of our API endpoints that we want to define. So what it's saying is whenever a GET request comes in for a path called /greet, what we're going to do is take a message and echo it back to the client in plain text. So this is a minimal HTTP server. Of course, your actual app will have many more routes, gets and posts and puts and things like that. You'll have a Fluent API to express it, although you can get down into the low-level objects and compose your routing rather than writing them all in line. Okay, so we have this code, we have this HTTP server. How do we build it and deploy it? You will have to learn a little bit of new stuff on Google Cloud in order to get this to run. The first thing you need to know is how to build a tag for your build. So this tag, think of this like a shell script. The shell script is defining a project ID, your project ID, a service ID that you've defined, and the tag is concatenating that with gcr.io. So gcr.io is basically googlecloudrun.io, kind of a namespace, your project, and then your service within that. This is a tag that's going to get applied to your build. You're going to run the gcloud command. Gcloud is Google Cloud's CLI. It's not the Firebase CLI. This is managed. This is a different CLI. What we're going to do is build our image and give it a tag. Now, what build submit is going to do is it's going to look for a Docker file in the current directory and start building the images based on what it sees in the Docker file. So this is going to generate a ton of output. You're going to see the Gradle build happen. You're going to see it pulling in all the dependencies. You're going to see it build the final Docker file, the Docker image. That Docker image isn't going to sit on your machine. It's actually going to get submitted to Google. And so it's going to live in Google's registry. Then to deploy that, you're going to run a second command, gcloud run deploy, give it the tag, say you want a fully managed platform, and that's it. Now your app is running. Now these commands, all told, will take a few minutes to run. It's not super rapid deployment. Cloud Functions is much more rapid, but Cloud Build takes more time. The upside with Cloud Run is that you basically can It's much easier to build and test your app locally than it is with Cloud Functions. With Cloud Functions, you have an emulator, but with Cloud Run, you basically just run the HTTP server and invoke it locally however you want. So with Cloud Run, you have to figure out what exactly do you want to run. If what I showed you today is not what you want, say you don't want Kotlin, maybe you want Java, maybe you don't want Ktor, maybe you want some other server, you have to figure it out. So you can choose pretty much any HTTP server you want. You can go fancy with Kotlin and use Ktor, or use a tiny web server called Nano HTTP. You can use a servlet container. So there's images that will give you a way to run on Tomcat, Glassfish, any one of the servlet containers that you already know if you're a J2EE developer. You can bring your own framework. So if you want to build a GWT app, that's fine. Spring, struts, whatever you want. Play if you're a Scala developer. Again, you're not really limited. You're basically defining the entire backend stack of technologies that you want to use. But what you do have to know once you've made all your decisions is you have to figure out what combination of language, runtime, and HTTP server of your choice. You have to make all those decisions. Cloud Run in their documentation gives you a bunch of sort of suggestions, but there's no opinionated nature on this. Google's not going to come out and say, you should be deploying X on Cloud Run. You really deploy whatever you want. You're going to have to learn how to build and modify a Docker file to create your container. As I showed you, Docker files don't have to be complicated. They're just saying how to assemble the final software of your image. You're going to have to figure out how to integrate your backend code with that container. So you have to figure out how to get the code once it's built into the container. And that's just a matter of copying a jar file, maybe. And you have to learn a few gcloud CLI commands. Another thing that's nice to know is how to build and test your container locally. So if you want to build your own Docker image, Docker itself has a CLI. You can run that CLI, you can build an image, and then you can emulate that image on your machine and invoke it directly to see how it works. That's actually kind of not necessary to know, but I like to play with things, and so it took me a day to figure out how to do this. It might be interesting for you to figure out how to do that yourself. So you might be thinking, well, okay, how does Cloud Functions compare with Cloud Run? We have two serverless options. They seem similar. Maybe they're different in some ways. I'll break it down. So with Cloud Functions, you have to choose a runtime of the supported ones. So you're going to basically choose either JavaScript, Go, or Python, or maybe Java whenever it's available. With Cloud Run, you have to choose a language and a runtime and an HTTP server. You have to choose those all. There's limitless options. With Cloud Functions, you're limited to what you can use. With Cloud Run, you write a Docker file. Then after you have that, you write code. After you've written the code for your app, you build a container with the code added, so that's for Cloud Run. You don't have a build, you notice you don't have a build step with Cloud Functions, all that's handled for you. Then you deploy. So you can see that Cloud Functions generally is easier to get started with. There are fewer steps. There's more guided paths. So you're basically choosing of a runtime and then just using that runtime the way that it was intended. With Cloud Run, you're constructing an entire server backend. In terms of capabilities and limits, as I said, Cloud Functions is limited. Cloud Run is basically unlimited. Cloud Functions, in my opinion, is easier to set up and deploy. Also, the Firebase CLI makes it super, super easy to deploy functions. Also, callable functions are a massive convenience, I think. With Cloud Run, I would say it's generally more difficult to set up and deploy. You don't get any conveniences. You don't get the event triggers. You have to proxy the event triggers into Cloud Run. With Cloud Functions, you can only deploy code to Google Cloud. So once you're using Cloud Functions, you're effectively locked into Cloud Functions. I mean, you can take your code and reuse it anywhere you want, but once you're deploying to Cloud Functions, you can't deploy elsewhere. There's only one destination. But with Cloud Run, once you know how to build that Docker image, you can take that Docker image and run it on any cloud you want. So if it's important for you to be able to change your cloud provider, definitely Cloud Run seems to be a better option. But if you want the short, sweet, and easy path, Cloud Functions is going to work for you better. Let's see, code can trigger with Firebase and Cloud Product. Oh, this is basically what I was saying. You don't get Cloud Functions, or you don't get event triggers with Cloud Run. You only get them with Cloud Functions. Now, it's worth saying a little bit about how these products scale. I said this is easy, scalable backends. What is it about Cloud Functions and Cloud Run that's so scalable? Well, the way it works is like this. If you have end users who are applying load to your product, either Cloud Run or Cloud Functions, what happens is Cloud Run or Cloud Functions will allocate server instances as needed in order to support that load. As the number of users increases, the number of backends increases. This is all transparent. You don't control any of this. You can't even really observe it. It just happens. And it will scale up as pretty much as high as you need. I know that for Cloud Functions, it will allocate up to 1,000 server instances per deployed function, which is a lot of server instances. If you need more than 1,000 concurrent server instances, you probably have a different scalability problem that can't be solved by cloud. I don't remember what the limits are for Cloud Run, but they both scale up and they scale down as needed. You don't have to do anything for that. Well, that's all I have. Is there any questions that I can help you with?